We're going to evaluate improper integrals today, which mean with bounds that go to infinity or negative infinity. So a couple things about the fundamental theorem of calculus. It requires that the function be continuous on the interval from a to b, and that the bounds are finite. So it means that we can't have an a or a b value that would go to infinity or negative infinity. The way we get around this is using an improper integral. So what we're going to do is if the bound goes to infinity, we will um, replace the bound with b and find the limit as b goes to infinity. We're going to do the same thing if the bound is negative infinity, except for instead we are going to replace our a value with, we're going to replace negative infinity with a and then take the limit as a goes to negative infinity. And then we can do this with both bounds being infinity or negative infinity and infinity by splitting up our integral into two limit integrals. All right, so what we're doing in these problems is figuring out if the area under the curve, okay, so if the area under the curve is finite, so if it goes to a certain value, or if it's going to grow forever. So if the area grows forever. So if the integral is said to converge, if the integral evaluates to a finite value, so just a number, and it diverges if the integral goes to infinity or cannot be determined. Okay. So then some things that we need to remember are that 1 over infinity is 1 divided by a gigantic number, which gives me basically 0. Okay. 1 over 0 to the negative 0 from the left is like 1 over negative 0.000001, for example. Okay. 1 divided by a very small number is going to give me a very small negative number is going to give me negative infinity. Okay. 1 over 0 positive, so 0 from the right, would be like 1 over positive 0.000001. So 1 divided by a very large number is going to go to positive, or 1 divided by a very small number will give you a very large portion, which is basically infinity. Okay. So we're going to start with an improper integral that diverges, so that means that we're going to end up going to negative infinity or positive infinity, basically. Okay. Or the area is undefined. Okay. So I have a bound of positive infinity. Remember, the bound has to be defined. So I'm going to write instead the integral from a to b of I like the dx on the side, so 1 over dx, 1 over x dx, and then I am going to substitute in later the limit as b goes to infinity. Okay, so I will evaluate this to be the limit as b goes to infinity of the integral of 1 over x is the ln of the absolute value of x evaluated from 1 to b. I'm going to substitute in my bounds, the limit as b goes to infinity of the ln of absolute value of b minus the ln of 1. I can drop the absolute value because 1 is positive. All right, so ln of 1 is 0. So I get the limit as b approaches infinity of the ln of absolute value of b. I am going to substitute in my infinity now, so I get to drop the limit. The ln of infinity minus 0 is, okay, ln of infinity is, ln looks like this. Remember, as x goes to infinity, y is also it's also steadily growing, so y is going to go towards infinity. So because the integral goes to infinity, we know that the integral diverges, meaning that the area is not finite. It's going to get bigger and bigger and bigger, the area under the curve. Okay, so this one, e to the x, looks something like this, okay? But we're going from, we're going from negative infinity to 0. So we want to know the area under the curve from negative infinity to 0, okay? So we want to know, is that like a finite amount of area, or is it just going to continually grow? So I have a problem because I have negative infinity as one of my bounds. So I'm going to write the limit, and I like to write a. So as a approaches negative infinity, and then the top bound I always use as b, but this one is a value, so I put 0. All right, e to the x dx. All right, I'm going to take the integral of e to the x, which is e to the x, evaluated from a to 0. And I need to remember that after I evaluate the integral by plugging in 0 and a, I'm going to take the limit. So I have the limit as a approaches negative infinity of e to the 0 minus e to the a, okay? And then we'll go ahead and substitute in negative infinity for a. So e to the 0 minus e to the negative infinity is e to the 0 minus 1 over e to the positive infinity. And e to the positive infinity is very large. So that is basically 1 over infinity. 1 over infinity is 0. So I have e to the 0, which is 1, minus 0. So the area under the curve that we mapped out right here is equal to 1. So the integral converges at 1. Okay, next. We have an upper bound of infinity. So I'm going to set up my upper bound as b. My lower bound is 0. So the limit as b goes to positive infinity of 1 over x squared plus 1 dx. And I am going to go ahead and take the integral, which I notice is 1 over x squared plus 1. So my u is equal to x, and my a is equal to 1. So the limit as b goes to infinity of arctan of x over a, so, or u over a, which is x over 1, so of x, evaluated from 0 to b. All right, go ahead and substitute in the value. Arctan of b minus arctan of 0, and then I bring down my limit because I can't forget that operation. All right, so we can plug in the infinity now. So the arctan of infinity minus the arctan of 0. And I remember that arctan looks like this, that it has an upper bound. It has a range of negative pi over 2 to pi over 2. And so as x goes to infinity, y is going to get close to the upper bound of pi over 2. And then the arctan of 0, that means that the ratio is 0. So the y over x ratio is 0. So that means that the y value has to be 0. So the angle of 0, or you can look at the graph and see that at 0, 0, you have a ratio of 0 and an angle of 0. So I see that pi over 2 is my answer. So the integral converges at x is at pi over 2. All right. Okay, here's a fun one. We're going to use L'Hopital. So upper bound is infinity. So I'm going to start with the limit as b approaches infinity of 1 to b of 1 minus x e to the negative x dx. Okay, I'm going to try and make a u substitution, but I see that if I make 1 minus x u, that the derivative of that is -1, and it's not going to cancel out e to the x, and then the derivative of e to the x is just e to the x, so it's not going to cancel anything else out as well. Enough out. So I think this is an integration by parts situation, and I have an exponential and an algebraic function. So I'm going to make my sines, my u, and my dv. So plus, minus, plus, minus. Make my u equal to 1 minus x, and my dv e to the negative x. The derivative of 1 minus x is -1. The derivative of -1 is 0. So I'm not going to need this last line. And then the antiderivative of e to the negative x is negative e to the negative x. And then I'm going to divide by this negative again, give me positive e to the negative x. And we can set up our integration by parts. So I have the limit as b approaches infinity of 1 minus x times negative e to the negative x plus -1. Negative gives me a positive, times e to the negative x. That was a little messy. Okay, so 1 times e to the negative x, and I'm evaluating from 1 to b. Okay, I'm going to rewrite this. So I have the limit as b approaches infinity of 1 minus x negative times 1 minus x over e to the x plus 1 over e to the x, evaluated from 1 to b. Okay, I'm going to go ahead and substitute. So I have the limit as b approaches infinity of, okay, substitute in b. So -1 minus b over e to the b plus 1 over e to the b minus -1 minus 1 over e to the 1 plus 1 over e to the 1. Okay, and I am going to simplify. So I notice that this negative time, so I'm basically subtracting 1 and then adding 1. So I have the limit as b approaches infinity of negative b over e to the b, because I'm going to combine these two fractions by adding. Okay, then this 1 minus 1 zeros. Okay, and then so I'm just subtracting out 1 over e, just regular e. Okay, from here, I'm going to plug in infinity to give me, I'm going to direct substitute to give me negative infinity over e to the infinity minus 1 over e. And I have a problem right here. This is an indeterminate. This is basically negative infinity over infinity, okay? And so I can apply L'Hopital. Okay, so I'm going to split up my limit to be the limit as b goes to infinity of negative b over e to the b minus the limit as b goes to infinity of 1 over e. And since, I can just evaluate the second one, it's just 1 over e. So I'm just going to go ahead and evaluate that to 1 over e. Okay. And for the second limit, L'Hopital, I take the derivative of, oh, I see I have a mistake. Okay, I did not distribute in the negative to the b, so the b should be positive here. Positive, positive, positive. I have infinity over infinity. Positive infinity over positive infinity. Okay? So again, L'Hopital, what we do is we take the derivative of the numerator, then separately the derivative of the denominator. So I have the limit as b goes to infinity. The derivative of b is 1. The derivative of e to the b is e to the b. So now I can substitute in the infinity, giving me 1 over e to the infinity. And then I'm going to bring down my 1 minus 1 over e. E to the infinity, 1 over infinity is basically 0 minus 1 over e. So I see that the integral converges at negative 1 over e. Underline. Okay, last one like this is what happens if the upper and the lower bounds are both infinity, then we have to split up our integral into two functions. So I am going to decide that I'm going to split up my integral into negative infinity to 0 of e to the x over 1 plus e to the 2x dx plus the integral from 0 to infinity of e to the x over 1 plus 2, I don't know why I keep doing that, e to the 2x dx. And now we can apply the limit to each one of those integrals. So I will go ahead and say that the limit as a approaches negative infinity of the integral of a to 0 of e to the x over 1 plus e to the 2x dx plus the limit as b approaches positive infinity of 0 to b of e to the x over 1 plus e to the 2x dx. We can honestly split this integral at any value here, but 0 seemed like a good place. It seemed like an easy number to substitute in, so that's why I use 0. But you can choose whatever you want, wherever you want to make the break. Okay. All right. So I am going to take a look at just my integral on the side. So I have the integral of e to the x over 1 plus e to the 2x dx, and I'm going to figure out how to solve this. So I'm going to start with u is equal to e to the x, because I think I see something. The derivative of e to the x is e to the x dx, so dx is equal to du over e to the x. So I'm going to go ahead and substitute in u over 1 plus u squared, since it's e to the 2x, times du over e to the x. And remember, e to the x is u, so u and e to the x cancel. giving me the integral of 1 over 1 plus u squared du, which is arctan of u over a, so u, which is plus c, so it's arctan of e to the x plus c. Okay, so I did that on the side so I wouldn't have to do it in my work. Okay, so I am going to take the integral of e to the x over 1 plus e to the 2x, which I now know is arctan of e to the x evaluated from a to 0 plus the limit of, as b approaches infinity, of arctan of e to the x evaluated from 0 to b. Okay, so next up, we go ahead and substitute in our bounds. So I have the limit as a approaches negative infinity of arctan 0 minus, arctan of e to the 0 minus arctan of e to the a plus the limit as b approaches infinity of arctan of e to the b minus arctan of e to the 0. Okay, cool. E to the 0 is 1. And so I am going to go ahead and apply my limits now. So I have the arctan of 1 minus the arctan of e to the negative infinity, which is 1 over e to the infinity, plus arctan of e to the positive infinity minus arctan of 1. Cool. Arctan of 1 minus arctan of 1 is 0. Arctan of 1 over infinity is basically the negative arctangent of 0 plus arctan of infinity. So remember back in our last example, or previous example, we are, as x goes to infinity, we are approaching the asymptote pi over 2. And the arctan of 0 is 0. So plus 0. So I end up with pi over 2. So the integral converges at pi over 2. Okay, that's it.